In section 8.2, we're going to look at magnetic force on moving charges. The unit of magnetic field strength is the Tesla. 1 Tesla is equal to 1 kilogram per Coulomb second. I want to compare 3 different examples of magnetic field strength. We can look at the magnetic field near the Earth's surface. This is not often something that we experience or can feel. If we have, say, metal, we don't feel a strong attraction of this metal to the Earth's surface. And that's because the magnetic field strength is really small. It's 5 times 10 to the power of negative 5 Tesla. A refrigerator magnet is much stronger. And its magnitude, the magnetic field strength, is 0.001 Tesla. So even though this is a comparatively stronger magnet than the Earth's magnetic field, it still has a small value for its magnetic field strength. Something that has a very strong magnetic field strength, like an MRI unit, only has a magnetic field strength of 7 Tesla. Now, keep in mind, 7 Tesla is very strong, but comparatively speaking, these magnitudes aren't very big, but they correspond to big changes in magnetic field strength. Whenever you have a charge in a magnetic field, the magnetic force exerted by a magnetic field on a moving charge with a velocity v can be found by using this equation. Magnetic force is equal to qvb sine theta, where q is the magnitude of the charge, v is the magnitude of the velocity of the charge, b is the magnitude of the magnetic field, and theta is the angle between the velocity and the magnetic field. We have a right-hand rule for a moving charge in a magnetic field. If you point your right thumb in the direction of the velocity of the charge, so if we look at our diagram, your right thumb is in the direction of the velocity of the charge, and your straight fingers point in the direction of the magnetic field, then your palm will point into the direction of the resulting magnetic force. So the magnetic force, if you line it up with your right hand, will come out of your palm. Now, if the charge is positive, like a proton, then the charge will come out, or the force rather, will come out of your palm and be pointing up. If the charge is negative, then the charge will be pointing down from the top of your hand or opposite from your palm. Okay, so keep this in mind as well. There's a difference as to whether or not the charge is positive or negative. Let's try a sample problem to put the right-hand rule for a moving charge in a magnetic field into practice. Sample problem number 1. The electron in figure below moves at a speed of 54 meters per second through a magnetic field with strength of 1.2 Tesla. The angle between the electron's velocity vector and the magnetic field is 90 degrees. Assume the value for the electron's charge is negative 1.6 times 10 to the power of negative 19 coulombs. So, we want to find the magnitude of the magnetic force. And we know it's equal to qvb sine theta. Now, the magnitude of the magnetic force can be found by using the charge. And the charge of an electron is negative 1.6 times 10 to the power of negative 19 coulombs. But we're only going to put in the magnitude of this, 1.6 times 10 to the power of negative 19 coulombs, and not the sign, because we're concerned with the magnitude, not the direction at this point. The speed in the question is 54 meters per second. The strength of a magnetic field is 1.2 Tesla. And we're looking at an angle of 90 degrees, so we have the sine of 90 degrees. If you punch this into your calculator, you should get a value of 1 times 10 to the power of negative 17 newtons. Therefore, the magnitude of the magnetic force on the electron is 1 times 10 to the power of negative 19 newtons. Okay, in part B, they want us to use the right-hand rule to determine the direction of the magnetic force. So I'm going to draw a diagram, and we have to line up our thumb with the velocity and our straight fingers in the same direction as the magnetic field. Now it's important for us to be able to visualize whether it's the palm of our hand facing down into the page or out into the page. So you have to make sure that you're using your right hand. In order to do this, to indicate, I'm going to draw in fingernails showing that we are placing this hand with our palm onto the page. Another thing that I'll do to reinforce the direction is to draw a clock, or a watch rather, and this watch will be indicating the top of your hand. Okay, so if you line up your right hand such that your thumb lines up with the velocity and your fingers line up with the magnetic field, then the right-hand rule tells us if Q is greater than 0, then F comes out of your palm in this case, it would be into the page. But we're not dealing with a positive charge. We are dealing with a negative charge. So Q is less than 0. So in this case, it'll be the opposite. So the force will come from the top of your hand. Therefore, out of the page. I don't know why I'm switching between square brackets and round brackets. Apologize. So, our statement, using the right-hand rule and the fact that electrons have a negative charge, so Q is less than 0, then the magnetic force points out of the page. In part C, they want us to calculate the gravitational force on the electron. And they give us the mass of the electron. It's 9.11 times 10 to the power of negative 31 kilograms. And I'm assuming they're starting this discussion comparing magnetic force to electric force or gravitational force rather, just to compare the relative magnitudes. It's important when we're talking about the fundamental forces of the universe to know that the weakest of all these forces is gravity, and that any other fundamental force, including magnetic force, will have a much larger magnitude. So let's find the gravitational force. It's equal to the mass of the electron times the gravitational field intensity. That's 9.11 times 10 to the power of negative 31 kilograms. And G is 9.8 newtons per kilogram. If you punch this into your calculator, you should get gravitational force of 8.9 times 10 to the power of negative 30 newtons. A super small force that the Earth attracts this one electron. Now, what's the ratio of the gravitational force to the magnetic force? Well, we've done these comparative calculations before where we just set up a ratio 8.9 times 10 to the power of 30 newtons for the magnetic, or the gravitational force rather. And the magnetic force is 1 times 10 to the power of negative 17 newtons. If you punch this into your calculator, you get 8.6 times 10 to the power of negative 13 to 1. So we can see that the gravitational force is significantly smaller than the magnetic force on the same electron. Okay, let's try sample problem number 2. A proton, and I'm just going to write off to the side here, Q is greater than 0. That will affect our right-hand rule for charges and magnetic fields, is moving along the x-axis at a speed of 78 meters per second. It enters a magnetic field of strength 2.7 Tesla. The angle between the proton's velocity vector and the magnetic field is 38 degrees, and the mass of the proton is 1.6 times 10 to the power of negative 27 kilograms. Calculate the initial magnitude and direction of the magnetic force on the proton. Let's start with the magnitude. Magnetic force is equal to QVB sine theta. Q is 1.6 times 10 to the power of negative 19 coulombs. It's a proton, so we know it's charge. We're not including a sign because we're concerned with the magnitude. The speed is 78 meters per second. That's given in the question. Magnetic field strength is 2.7 Tesla. The angle between velocity and magnetic field is 38 degrees. If we punch this in, we will get a magnitude of 2.1 times 10 to the power of negative 17 newtons. So we have the magnitude of the magnetic field. Now what we need to do is find the direction. Remember, your thumb on your right hand needs to line up with the velocity, and your straight fingers need to line up with the magnetic field. So it's important to twist your hand so that you have this in the proper orientation. I'm going to draw a diagram that'll hopefully elicit this. So we can see it clearly. So here is our thumb. And here are our straight fingers. Apologize for these drawings, guys. They're not my best. Is that the correct number of fingers? Yes. And just so you can see, the palm of your hand is facing upward and out of the page. The person is wearing a watch, but in this case, you can't see the watch face. You can only see the buckle. I don't know if this is helpful to you, but I enjoy drawing diagrams, so I'll do them whenever I can. So, since it's a positive charge, the force should come out of the palm. Okay? And therefore, I'm just going to clean this up so you can see this better. Since Q is greater than 0, this force should come right out of the palm. And I'm just going to decline this call in the background. All right. So the direction of the magnetic force is out of your hand. Now, in part B, they want us to determine the proton's initial acceleration. Acceleration will be equal to the magnetic force acting on this proton divided by the mass of the proton. So that's 2.1 times 10 to the power of negative 17 newtons divided by the mass of the proton, which is 1.6 times 10 to the power of negative 27 kilograms. If you punch this in, you should get 1.2 times 10 to the power of 10 meters per second squared. Don't forget to square it. All right. In the last problem, we're going to look at determining the effect of the Earth's magnetic field on the direction that lightning strikes. During a thunderstorm, positive charge accumulates near the top of a cloud and negative charge accumulates near the bottom. When the charge buildup is strong enough, negative charge moves rapidly from the cloud to the ground as a lightning strike. Assume the charge velocity vector is perpendicular to the ground and the Earth's magnetic field is horizontal, directed north. Determine the direction and deflection of this charge by the Earth's magnetic field. Okay, we're going to use the right-hand rule for charges in a magnetic field to determine this. We have to line up our thumb in the direction of the velocity, and we're going to line up our straight fingers in the direction of the magnetic field. I will draw another diagram. Hopefully this will help us to understand and see. So your thumb has to be in this direction. And if you're dealing with your right thumb, you'll realize that in order for this to work, the top of your hand has to be facing the outside of this page. And your fingers, your straight fingers, should be pointed in the direction of the magnetic field. And I'm going to draw our watch face. So we'll be able to see the watch on the top of our hand. And I'm just going to pull this diagram out to the side so we can see it a little clearer. So the right-hand rule, and again, I apologize, these aren't my best drawings. The right-hand rule tells us that if the charge is positive, then the charge should come out of your palm. And since we're looking at the positive charge moving, we know that when lightning strikes, the Earth magnetic field deflects the charge towards, in this case, out of our palm. And if we look, this is west, this is north, this would be east, and this would be south. So we can say that the charge will be pushed towards the west. Okay, that'll be the direction of the magnetic force. Okay. This requires some visual spatial understanding and some contorting of your wrist and your hand. Hopefully you can do this quite easily. Please practice questions on page 390 and 391, and good luck.